There is something about this question that should disturb you. It seems so simple that almost everyone believes they already understand it, yet the longer you remain with it, the more the ground beneath your certainty begins to disappear. We are taught that every story has a beginning, every road has a first step, every life has a moment before which it did not exist. Naturally, we ask the same thing about the universe. What was there before the Big Bang? But what if that question is not simply unanswered? What if it is asking reality to reveal something that reality itself refuses to define? Every morning, without thinking about it, you wake up inside a universe that appears stable. The floor beneath your feet feels solid. Time moves forward with quiet confidence. Clocks tick. Shadows slowly shift. People grow older. Stars rise and disappear beyond the horizon. Everything around you suggests that existence unfolds like a story written across an invisible timeline, where one event follows another, every effect has a cause, and every beginning must have something before it. Yet the moment we stretch that intuition all the way back to the birth of the cosmos, something extraordinary happens. The rules that seem unquestionable in everyday life begin to dissolve. The closer physics looks toward the first moments of existence, the less familiar reality becomes. The universe starts behaving less like a machine and more like a mystery that was never designed for human intuition. The question becomes impossible to ignore. If the Big Bang marked the beginning of everything we know, what existed before it? Was there another universe? An endless void? A timeless state? Or is the entire idea of before nothing more than a habit inherited from the way our minds experience time? That possibility is far stranger than it first appears. If you're new here, welcome. Subscribe, settle in, and follow this question with us as far as science can honestly take it, because the deeper we go, the more it begins to reshape not only our understanding of the universe, but our understanding of reality itself. Think for a moment about something completely ordinary. Imagine opening a book. Before the first page, there is a cover. Before the cover, there was a printing press. Before that, there were trees. Every object you have ever touched belongs to an endless chain of causes. Your mind has spent an entire lifetime learning that every beginning hides an earlier beginning. The idea is so deeply rooted that we rarely stop to notice it. So when someone says the universe began 13.8 billion years ago, almost everyone instinctively asks the same question. What happened 1 second earlier? It feels unavoidable. But this is also where intuition quietly becomes our greatest obstacle. The universe does not necessarily behave like the objects we use to understand it. A chair begins because someone built it. A mountain forms because tectonic plates slowly collide. A star ignites because gravity compresses clouds of gas until nuclear fusion begins. Every example from ordinary life teaches us that beginnings happen inside time. The Big Bang may not. That single distinction changes everything. The phrase, Big Bang, often creates the wrong image. Many people imagine an enormous explosion occurring somewhere inside an already existing emptiness, as though a cosmic bomb suddenly detonated in the darkness. Modern cosmology describes something profoundly different. The Big Bang was not an explosion inside space. It was the rapid expansion of space itself. There was no empty room waiting for galaxies to appear. Space was not a stage upon which the universe arrived. The stage itself was unfolding. This seems impossible only because our imagination insists on placing every event inside a larger container. We imagine fish swimming inside an ocean, planets moving through space, clocks measuring time. Naturally, we assume the universe itself must also exist inside something larger. Physics has never found evidence that this must be true. And here is the detail that changes everything. If space itself was expanding, then asking where the universe expanded into may be like asking what lies north of the North Pole. The question sounds meaningful because language allows us to ask it, but reality may not contain the thing the question assumes. Exactly the same problem appears with time. We instinctively imagine time as an invisible river flowing endlessly in both directions. We stand somewhere along its current, remembering the past while moving toward the future. The image feels so natural that questioning it almost seems absurd. But according to Einstein's theory of general relativity, time is not an independent river flowing outside the universe. Time is woven together with space into a single fabric known as spacetime. Matter bends it. Energy shapes it. Gravity is not simply a force pulling objects together. It is the geometry of spacetime responding to the presence of mass and energy. This realization transformed physics forever because it replaced the comforting image of a fixed cosmic stage with something alive and dynamic. Space can stretch. Time can slow. Distances can change. Even the passage of seconds depends on gravity and motion. Our intuition tells us one story. Physics tells another. Time is not an external clock watching the universe from somewhere beyond it. Time appears to be part of the universe itself. And if that is true, an unsettling possibility immediately emerges. Perhaps time itself began with the Big Bang. But this is still only the surface of the mystery. Because if time truly began there, then asking what happened before the Big Bang may resemble asking what happened yesterday before yesterday existed. The sentence is grammatically correct, yet the concept itself may not correspond to anything real. For decades, physicists have pushed mathematics to this boundary. As telescopes became more powerful, they looked farther into deep space, and every distant galaxy became a kind of ancient photograph. Because light takes time to travel, looking farther away also means looking farther back into cosmic history. The night sky is not merely filled with distant objects. It is filled with different moments of time. Every telescope is, in a sense, a machine built to observe the past. The most distant galaxies reveal a younger universe. Beyond them lies the faint glow known as the cosmic microwave background, the oldest light humanity has ever detected. It is often described as the afterglow of the early universe, a frozen echo from nearly 380,000 years after the Big Bang. But notice something remarkable. Even our oldest picture of the cosmos is not the beginning. It is already a universe that has cooled, expanded, and evolved. The true beginning remains hidden behind a boundary that light itself cannot cross. That invisible horizon marks one of the greatest limits in modern science. Everything we confidently describe happened after that boundary. Everything before it becomes increasingly uncertain. And this creates another puzzle. If physics successfully explains galaxies, stars, atoms, black holes, gravity, and the evolution of the observable universe with extraordinary precision, why does it struggle exactly where the story seems to begin? The answer is not that scientists have stopped searching. It is that the mathematics itself begins to fracture. As we rewind cosmic history closer and closer to the first instant, temperatures rise beyond imagination. Matter dissolves into pure energy. The fundamental forces that govern nature begin behaving in ways our current theories cannot fully reconcile. Space becomes compressed beyond anything we can truly picture. Eventually, our equations predict something known as a singularity, a point where density becomes infinite, curvature becomes infinite, and the known laws of physics lose their ability to describe reality. But here is the problem. Many physicists no longer believe that this singularity is a physical object waiting somewhere in the distant past. Instead, they see it as a warning. Not a place where reality ends, but a place where our current understanding reaches its limit. And if our theories fail precisely where we most want answers, then perhaps the greatest mystery is not what happened before the Big Bang. Perhaps the deeper mystery is why the universe allows us to understand almost everything, until we arrive at the moment where understanding itself begins to disappear. Our confidence begins to dissolve the moment we arrive at the singularity. For many people, it seems like the ultimate answer, the final destination reached by every equation that traces the history of the universe backward through time. But many physicists see it differently. They do not believe the singularity is a real object hidden at the beginning of existence. Instead, they see it as a warning sign, a place where our mathematical descriptions stop working, revealing not the end of reality, but the limits of our understanding. That distinction changes everything. Imagine trying to cross a vast mountain range using nothing more than a map of the oceans. The moment the map stops making sense does not mean the mountains disappear. It simply means the map has reached the edge of its usefulness. In much the same way, Einstein's theory of general relativity has proven to be one of the most successful scientific achievements in history. It predicts the motion of planets, the bending of light around massive objects, the existence of black holes, and even the gravitational waves that ripple through the fabric of spacetime. Every observation continues to reinforce its extraordinary accuracy. Yet even the greatest theories have boundaries. General relativity describes gravity with remarkable precision on the largest scales imaginable. It explains how stars form, how galaxies evolve, and how the universe expands across billions of light years. But as we travel backward toward the earliest fraction of a second after the Big Bang, everything changes. Matter becomes unimaginably dense, temperatures climb beyond comprehension, and the smooth geometry described by Einstein begins to collide with another set of rules entirely. The rules of the quantum world. This is where the mystery becomes even stranger. Quantum mechanics governs reality at scales so small that ordinary intuition becomes almost useless. At this level, certainty gives way to probability. Particles no longer behave like tiny solid objects following perfectly defined paths. Instead, they are described by mathematical probabilities, existing in ways that challenge the very language we use to describe reality. The deeper physicists looked into this hidden world, the more they realized that nature is far less predictable than it appears from our everyday perspective. But perhaps the most astonishing discovery is that empty space is not truly empty. Our intuition tells us that nothing should contain absolutely nothing. Physics tells a completely different story. According to quantum field theory, what we call the vacuum is not an empty void. It is an invisible sea of energy where quantum fields constantly fluctuate. Tiny particles briefly emerge into existence and disappear again almost instantly. These fleeting events occur continuously throughout the universe, even in regions where no stars, no planets, and no matter seem to exist. This is not science fiction. These fluctuations produce measurable effects that have been confirmed through precise experiments, suggesting that what appears to be complete emptiness is actually filled with restless activity beyond ordinary perception. Now consider what that implies. If the emptiness of today's universe already possesses this hidden structure, what was reality like when the entire observable universe was compressed into a volume smaller than an atom? What happened when every quantum fluctuation existed under conditions far more extreme than anything our laboratories could ever reproduce? The truth is that we do not yet know. And in science, uncertainty is not failure. It is the beginning of discovery. For decades, physicists have searched for a theory capable of unifying the two greatest descriptions of nature ever created. General relativity explains gravity and the behavior of the cosmos on the largest scales. Quantum mechanics governs the smallest building blocks of reality with astonishing precision. Separately, both theories work remarkably well. Together, they refuse to fit. Somewhere in that gap lies one of the greatest unsolved problems in modern physics. A complete theory of quantum gravity. Such a theory would describe gravity not as Einstein saw it alone, nor as quantum mechanics describes particles alone, but as part of a deeper framework capable of explaining the universe under the extreme conditions that existed at its earliest moments. No one has succeeded yet. Several promising ideas exist, but none has been experimentally confirmed. That is why the question of what came before the Big Bang remains open. Because before we can answer what happened, we may first have to understand what space and time truly are. Think about the way we describe spacetime. We often compare it to a fabric, a smooth surface that bends under the influence of mass and energy. It is a useful image, but it quietly hides another question. Fabric is woven from threads. Sand is made from grains. Water is made from molecules. So what is spacetime made of? Perhaps that question sounds strange only because we have become accustomed to imagining space as something continuous. But several approaches to quantum gravity suggest that spacetime itself may possess an incredibly fine microscopic structure, composed of fundamental units so unimaginably small that they remain invisible to every instrument humanity has ever built. From a great distance, a beach appears perfectly smooth. Only when you kneel down do you discover that it is made of countless individual grains of sand. Some physicists suspect spacetime may work in exactly the same way. If this idea is correct, then the smooth universe described by Einstein may be only an approximation, much like the calm surface of the ocean hides the countless molecules moving beneath it. And here is the detail that changes the entire conversation. If spacetime itself emerges from something more fundamental, then perhaps the Big Bang was not the birth of space and time at all. It may have been the moment when a deeper level of reality transformed into the universe we observe today. The idea sounds almost impossible. Yet it emerges not from fantasy, but from serious attempts to solve mathematical problems that current physics cannot ignore. But before we descend even further, we must examine another assumption that quietly shapes every question we ask. Causality. Everything in your experience follows the same pattern. A seed becomes a tree. A glass falls because someone lets go. A fire begins because something ignites it. Causes always seem to come first, and effects always seem to follow. It feels like one of the most fundamental truths imaginable. But causality depends on time. Without time, the distinction between before and after becomes meaningless. This is where intuition encounters another invisible wall. If time itself emerged during the earliest moments of the universe, then asking what caused the Big Bang may accidentally assume that causality already existed before the conditions that allow causality to exist. The mistake lies in imagining that the universe must begin in the same way ordinary objects begin. Reality may not obey that expectation. Imagine standing at the North Pole. You can walk south in countless directions, but asking someone to point farther north no longer makes sense. The question fails not because the answer is hidden, but because the geometry itself has reached its natural limit. Some cosmologists believe time near the Big Bang may behave in a remarkably similar way. The earliest moment of the universe could represent a boundary beyond which the concept of before simply loses its meaning. This possibility is profoundly uncomfortable because our minds are built around sequence. Every memory belongs to the past. Every expectation belongs to the future. Every language on Earth reflects that order. Yet history has repeatedly shown that reality does not care about human intuition. The Earth feels motionless, yet it races through space. Matter feels solid, yet atoms are mostly empty. Time feels universal, yet relativity reveals that it flows differently depending on gravity and motion. Again and again, physics has forced us to abandon ideas that once seemed undeniable. Perhaps our understanding of time is simply the next illusion waiting to be replaced. But even if the phrase, "before the Big Bang," turns out to have no physical meaning, another mystery immediately appears. Why does a universe exist at all? Why do the laws of physics possess precisely the form they do? Why is there something capable of generating space, time, matter, and energy instead of absolute nothingness? Notice how far the question has evolved. We began by asking about an event in the distant past. Now we are questioning the foundations of existence itself. This is the point where cosmology slowly meets philosophy without leaving the discipline of science. Physics can describe the evolution of the universe with extraordinary accuracy after its earliest measurable moments. It can explain the formation of light elements, predict the cosmic microwave background, and trace the growth of galaxies across billions of years. But the closer we approach the deepest foundations of reality, the more every answer seems to uncover another question hidden beneath it. And then comes one of the most remarkable ideas in all of modern cosmology. Shortly after the universe came into existence, something extraordinary may have happened. According to the theory of cosmic inflation, the young universe underwent an almost unimaginable burst of expansion, growing from microscopic scales to astronomical dimensions in an incredibly tiny fraction of a second. This theory explains several puzzles that otherwise seem almost impossible. It helps us understand why regions of the universe separated by immense distances share nearly identical temperatures. It explains why the geometry of the observable universe appears so remarkably flat. Most astonishing of all, it suggests that tiny quantum fluctuations in the infant cosmos eventually became the galaxies, stars, planets, and ultimately the observers capable of asking where everything began. But here is the detail that changes everything once again. Inflation does not explain the beginning. It explains what may have happened immediately after the earliest moments physics can currently describe. One mystery has simply been replaced by another. What triggered inflation? What conditions allowed it to start? Did it emerge from an earlier state of reality? Or is inflation itself only one chapter in a story whose first pages remain forever hidden beyond the reach of our current understanding? To approach those questions, we must descend another level, into ideas so unfamiliar that they challenge not only our picture of the universe, but the very meaning of beginnings themselves. As we descend another layer into this mystery, the language of ordinary experience begins to lose its meaning. Up to this point, we have followed ideas that, although unfamiliar, still preserve a recognizable picture of reality. Space expands. Time bends. Gravity shapes the geometry of the cosmos. Quantum fields ripple beneath what appears to be empty space. Each concept stretches our intuition, yet they all belong to a universe that still feels, in some sense, understandable. The next step is different. Here, even the idea of a beginning becomes uncertain. If cosmic inflation explains only what happened immediately after the earliest moments we can describe, then another question naturally emerges. What created the conditions that allowed inflation to begin? Was there an even earlier state of reality? Or have we simply reached a point where the idea of a first moment no longer makes sense? These are no longer philosophical thought experiments. They are questions that arise from real mathematical attempts to solve some of the deepest problems in modern physics. One of the most intriguing possibilities is known as the bouncing universe. At first, the concept seems surprisingly simple. Instead of imagining the Big Bang as the absolute beginning of everything, some cosmological models propose that it was actually a transition. Long before the universe began expanding, it may have been doing the opposite. Space could have been slowly contracting over unimaginable stretches of time. Galaxies, stars, and eventually the very fabric of spacetime would have drawn closer together as the cosmos became increasingly dense. Our intuition tells us that such a collapse should inevitably end in a singularity, where density becomes infinite and the laws of physics break down completely. But some theories suggest something very different. According to these models, quantum effects, or forms of gravity we have not yet fully understood, could prevent the universe from ever reaching infinite density. Instead of collapsing into an impossible point, the contraction would eventually stop. Then everything would reverse. The universe would bounce. Contraction would become expansion. The event we now call the Big Bang would not represent the birth of reality itself, but the moment one cosmic era transformed into another. This possibility changes the meaning of the question entirely. Perhaps the universe did not emerge from nothing. Perhaps what appears to us as a beginning is actually part of an endless rhythm, much like the beating of a heart or the waves of an ocean. Every wave seems to be born and die, yet the ocean itself never begins with any single wave. Every heartbeat feels like a new event, yet it belongs to a continuous cycle that stretches beyond any individual beat. Some cosmologists wonder whether our universe could resemble that ocean far more than it resembles a single cosmic explosion. But this is where science demands caution. Current observations have not confirmed this picture. Some bouncing models reproduce many of the features we observe in today's universe while avoiding the mathematical singularity predicted by general relativity. Others encounter serious theoretical difficulties or fail to match astronomical observations with sufficient accuracy. The idea remains a scientific hypothesis. A fascinating one. But still a hypothesis. That uncertainty is not a weakness. It is exactly how science progresses. Beautiful ideas survive only if nature agrees with them. And nature has often surprised us. The mystery becomes even stranger when we consider another possibility that has become one of the most discussed concepts in modern cosmology. What if our universe is only one region within a far larger reality? This idea is commonly associated with the multiverse, although it is often misunderstood. Popular culture frequently imagines an infinite collection of alternate realities where every imaginable version of history exists somewhere. The scientific discussion is far more careful. Some versions of cosmic inflation suggest that inflation may not have ended everywhere at the same time. While it stopped in the region that became our observable universe, it could still be continuing elsewhere. Vast regions of spacetime might still be expanding, occasionally producing enormous, bubble universes, each separated from the others by distances so immense that they may never interact. If this picture is correct, our universe would be just one bubble within an unimaginably larger cosmic landscape. Each bubble could possess different physical conditions, different values for the fundamental constants, perhaps even different laws governing the behavior of matter and energy. Notice what happens to our original question. Instead of asking what existed before the Big Bang, we are now forced to ask what kind of reality gives birth to universes themselves. The mystery moves once again. Every answer uncovers another, deeper question waiting beneath it. This pattern should feel familiar. Humanity once believed Earth occupied the center of existence. Then we discovered the solar system. The solar system became one small system within the Milky Way. The Milky Way became one galaxy among hundreds of billions spread across the observable universe. Every apparent center eventually dissolved into something larger. Perhaps the Big Bang is simply the next center waiting to disappear. But this is only one path the mystery can take. Another emerges from the strange foundations of quantum mechanics itself. At the smallest scales known to physics, reality refuses to behave like the world we experience every day. Particles no longer resemble tiny objects moving along precise trajectories. Instead, they exist as quantum states described by probabilities, interacting through mathematical relationships that have no direct counterpart in ordinary life. Our intuition insists that every object must always possess definite properties. Quantum mechanics repeatedly challenges that belief. This has led some physicists to propose that the universe itself may have emerged through a quantum process. According to certain models, the earliest universe existed not as ordinary space and time, but as a quantum state from which classical spacetime eventually emerged. If that picture is correct, then asking what existed before the Big Bang may be similar to asking what existed before a wave appeared on the surface of the ocean. The wave has a beginning. The ocean does not. In this analogy, the ocean would not be made of water, matter, energy, or even time as we understand them. It would represent something even more fundamental. Something from which space, time, and the laws of physics themselves could emerge. This possibility is extraordinarily difficult to imagine because the human brain evolved to understand objects, landscapes, movement, and survival, not the deepest architecture of reality itself. Once again, intuition reaches its limit. Our minds instinctively search for familiar images. Reality may simply refuse to provide them. This becomes especially important when we use the word nothing. In everyday language, nothing means the complete absence of everything. No matter. No energy. No light. No space. No time. But physics uses that word much more carefully. A quantum vacuum is often described as empty, yet it still contains quantum fields, measurable energy, and constant fluctuations governed by mathematical laws. Whatever this state represents, it is certainly not absolute philosophical nothingness. That distinction matters enormously. People sometimes say that the universe came from nothing, but many scientific models actually describe the universe emerging from highly structured quantum states that already possess physical properties. The deeper question therefore remains untouched. Why do those quantum fields exist? Why do mathematical laws exist at all? Why is there a framework capable of producing universes instead of absolute non-existence? Notice how every solution seems to push the mystery one step farther away. Each answer becomes the doorway to another question. Far from being a failure, this endless progression is one of the defining strengths of science. Science does not claim certainty where certainty cannot yet be justified. It constructs models. It compares predictions with observations. It abandons ideas that fail. It refines those that survive. The frontier of knowledge is built not upon confidence, but upon disciplined uncertainty. And nowhere is that more evident than in cosmology. The more carefully we observe the universe, the more extraordinary its story becomes. Tiny quantum fluctuations in the earliest moments of cosmic history eventually became galaxies. Gravity gathered matter into stars. Inside those stars, heavier elements were forged through nuclear fusion. When massive stars died, they scattered those elements across space. New generations of stars and planets formed from that ancient material. Eventually, on one small world orbiting an ordinary star, chemistry became biology. Biology became consciousness. And consciousness began asking questions about events that occurred billions of years before the Earth itself existed. That alone is astonishing. The atoms inside your body were created in stars that lived and died long after the earliest moments of cosmic history. Yet those same atoms are now organized into a mind capable of questioning the origin of the universe itself. It is almost as if the cosmos spent billions of years constructing a mirror through which it could examine its own beginning. But perhaps the most humbling realization is this: that mirror may never reveal the entire picture. There may be limits built into reality itself, limits imposed not by technology, intelligence, or imagination, but by the very structure of the universe. Just as no telescope can see beyond the observable horizon simply by becoming larger, there may be questions whose complete answers remain permanently hidden behind boundaries established by the laws of physics themselves. If that is true, then the greatest challenge facing science is not discovering every answer. It is learning where the horizon of explanation truly ends. And yet, even that horizon may not be the final one. Because the next layer of this mystery asks something even more profound than what existed before the Big Bang. It asks whether we have been looking in the wrong direction all along. What if, after everything we have explored, we have been asking the wrong question from the very beginning? It is an unsettling possibility, because throughout this journey we have treated the universe as though it must behave like every object we have ever known. We have assumed that it must have started at a particular moment, from a particular cause, following a sequence that could eventually be reconstructed if only our science became advanced enough. Every question we have asked has quietly depended on that assumption. But what if the assumption itself is the final illusion? At this point, the mystery is no longer only about cosmology. It becomes a question about the limits of human thought itself. The language we use every day evolved to describe a world of falling stones, flowing rivers, changing seasons, and living creatures. Every sentence naturally arranges events into an order. Something happens first, something else happens afterward. Every explanation depends on a timeline that feels so obvious we almost never stop to question it. Yet the universe may not share the grammar of our minds. The mistake may not be in our mathematics, but in our intuition. We instinctively expect reality to fit the concepts that helped our ancestors survive on a small planet orbiting an ordinary star. But history has repeatedly shown that nature is under no obligation to satisfy those expectations. Once, humanity believed the Earth stood motionless at the center of creation. Then we discovered it was moving. We believed space was fixed and unchanging. Then Einstein showed that space itself bends, stretches, and responds to matter and energy. We believed time flowed equally for everyone. Relativity revealed that even the passage of time depends on motion and gravity. We believed matter was solid. Quantum physics revealed that atoms are almost entirely empty space, held together by invisible fields and governed by probabilities rather than certainty. Again and again, every major breakthrough in physics has forced us to abandon an intuition that once felt impossible to doubt. Perhaps the next intuition waiting to be replaced is the belief that reality itself must have a beginning in the way we imagine beginnings. That sounds almost impossible to accept, but only because our entire experience of consciousness unfolds one moment after another. We remember yesterday. We experience today. We anticipate tomorrow. Life feels like a spotlight moving across an endless landscape of time. But several interpretations of modern physics suggest something profoundly different. According to one view, the universe is not a story unfolding page by page. Instead, spacetime may exist as a complete four-dimensional structure in which past, present, and future are equally real. From this perspective, the sensation that time is flowing could emerge from the way conscious beings experience reality rather than from time itself physically moving forward. Our intuition says that only the present truly exists. The mathematics allows for a far stranger possibility. If this picture reflects even part of reality, then asking what happened before the Big Bang may be like asking what lies north of the North Pole. The question appears meaningful because language allows us to ask it, yet it assumes a direction that may not exist. But even if the concept of before loses its meaning, one extraordinary mystery remains untouched. There is still a universe. It follows elegant mathematical laws. Those laws permit extraordinary complexity to emerge from astonishing simplicity. Hydrogen formed in the early universe. Gravity gathered hydrogen into stars. Inside those stars, nuclear fusion forged heavier elements. Exploding stars scattered those elements across space. Planets condensed from ancient clouds of stellar debris. On at least one of those planets, chemistry slowly became biology. Biology eventually became consciousness. And consciousness began asking why any of this exists at all. That chain of events is so extraordinary that we sometimes overlook its significance. The universe did not merely become large enough to contain galaxies. It became structured enough to produce observers capable of wondering about its own origin. That realization has inspired some of the deepest questions in both physics and philosophy. Why do the laws of nature possess the values they do? Why do the fundamental constants appear to allow complex matter, stars, chemistry, and eventually life? Some researchers suggest that deeper physical principles may eventually explain these values naturally. Others propose that if countless universes exist, each with different physical constants, then we inevitably find ourselves in one capable of supporting observers simply because no one could exist in the others. Neither possibility has been confirmed. Both remain active frontiers of scientific research. And this distinction is essential. One of science's greatest strengths is not its ability to provide immediate answers, but its discipline in separating evidence from speculation. At the frontier of knowledge, intellectual honesty becomes more valuable than certainty. The greatest physicists are often the first to acknowledge where the equations stop, where observations become incomplete, and where imagination must patiently wait for new evidence. That humility is not a weakness. It is precisely what allows science to move forward. History reminds us that mysteries once believed impossible to solve eventually surrendered to deeper understanding. The motion of the planets, the nature of life, the existence of atoms, the expansion of the universe, black holes, and gravitational waves all began as ideas that seemed almost beyond belief before evidence transformed them into accepted science. Perhaps one day the mystery of what came before the Big Bang will follow the same path. Or perhaps it will reveal something even more unexpected. Perhaps there was never a before. Perhaps our universe emerged from an earlier cosmic cycle. Perhaps it was born from a quantum state beyond spacetime. Perhaps it is only one region within a much greater cosmic landscape that continuously gives rise to new universes. Or perhaps the true explanation belongs to a theory humanity has not yet discovered. Every one of these possibilities remains incomplete. Every one is constrained by mathematics, observation, and careful scientific reasoning. None has solved the mystery. And that is exactly what makes the question so extraordinary. Notice how different it has become from the moment we first asked it. At the beginning, we imagined ourselves searching for a hidden event that occurred before everything else. Now we understand that the real challenge lies much deeper. The true question is whether ideas like before, after, beginning, and even existence retain the meanings we casually assign to them when we attempt to describe the universe as a whole. The mystery has not become smaller. It has become infinitely larger. Somewhere beyond the observable universe, or perhaps woven into every point of spacetime itself, there may exist a deeper level of reality that our current theories can only glimpse through fragments of mathematics and subtle clues hidden within the cosmos. Every new telescope extends our vision. Every particle accelerator pushes our experiments further. Every improvement in cosmological observation sharpens our understanding. Yet with every discovery, the horizon seems to move farther away. It is like standing on the shore of an endless ocean. As you walk toward the horizon, the waves become clearer. The details become richer. But the horizon itself never grows any closer. That realization can feel frustrating if we expect science to deliver final answers. But it becomes deeply inspiring once we understand what science truly is. Science is not a collection of permanent truths. It is humanity's most reliable method for approaching mysteries without pretending they have already been solved. Every great discovery begins with a question that seemed impossible, asked by people willing to remain uncertain long enough to let reality answer on its own terms. Perhaps that is the greatest lesson hidden within the mystery of the Big Bang. The universe is under no obligation to match the stories our intuition tells us. Reality is older than language, deeper than imagination, and infinitely more patient than certainty. The next great breakthrough may arrive decades from now, or centuries into the future, born from equations not yet written, observations not yet made, or ideas that today seem as impossible as curved spacetime once seemed before Einstein revealed it. Until that day, we occupy a remarkable place in the history of the cosmos. We are temporary beings, living for only an instant on a small planet orbiting an ordinary star, yet somehow capable of measuring the oldest light in the universe, detecting ripples in spacetime itself, and asking questions that reach beyond the very edge of time. Few facts are more extraordinary than that. Perhaps the greatest mystery is not that the universe continues to guard its deepest secrets. Perhaps the greatest mystery is that a universe born from ancient light, expanding across billions of years, has somehow produced minds capable of wondering what existed before its own beginning. And maybe that is why this question refuses to disappear. Because every attempt to answer it reveals that the boundary we keep approaching is not only the edge of the observable universe. It is also the edge of human understanding. So the next time you find yourself asking what existed before the Big Bang, remember that the question is no longer the one we started with. It is no longer asking what came first. It is asking whether the idea of first was ever the right way to think about reality at all. And somewhere beyond the oldest light we can observe, beyond every equation we have written, and beyond every horizon our instruments can reach, the universe remains silent, not because there are no answers, but because the deepest truths may exist beyond the limits of the questions we have learned to ask.